Right now, you're moving faster than a jet fighter. At the equator, Earth spins at about 1,670 kilometers per hour. You don't feel it because everything around you moves at the same speed. But what if that spin simply stopped? Not slowed down. Stopped. What would actually happen to our planet? There are two very different versions of this scenario. One is a sudden stop, happening in an instant, which would be an almost unimaginable catastrophe. The other is a gradual stop over centuries, which is physically more plausible and, strangely, even stranger in its long-term consequences. We'll explore both. It's worth noting Earth isn't the only planet with unusual rotation. Venus spins so slowly, once every 243 Earth days, and even backwards compared to most planets, that a single Venusian day is longer than its entire year. Mercury, meanwhile, rotates only 3 times for every 2 orbits around the Sun. These slow-spinning worlds give scientists real data on what extreme rotation, or the near absence of it, does to a planet. Venus, for instance, has a scorching, crushing atmosphere partly shaped by its sluggish spin. Studying these neighboring planets helps researchers model more accurately what a non-rotating Earth might truly look like. Let's start with the instant scenario, because physics tells us something brutal right away. Newton's first law says objects in motion stay in motion unless acted on by a force. If the ground beneath you suddenly stopped, your body would not. You would keep moving at 1,670 kilometers per hour. That speed is faster than the speed of sound. Anything not bolted deeply into bedrock, buildings, trees, vehicles, people, would be hurled eastward with the force of a supersonic blast wave. Entire cities would be scoured off the map within seconds. This is not an exaggeration, it's basic mechanics. The atmosphere itself is also spinning with the planet. If the ground stopped but the air kept moving, hurricane-force winds far beyond anything ever recorded would rip across the surface. Some estimates put these winds at speeds comparable to the re-entry of a spacecraft. Nothing built by humans could withstand that. Oceans would behave the same way. The water covering 70% of our planet would keep moving at rotational speed even as the seafloor beneath it halted. This would trigger tsunamis unlike anything in recorded history, walls of water racing across ocean basins and slamming into every coastline on Earth. Within minutes of a sudden stop, we'd be looking at a planet-wide extinction event. Coastal civilization erased by tsunamis, interior regions scoured by supersonic winds, and an atmosphere thrown into complete chaos. Scientists generally agree that a sudden stop would make the surface uninhabitable almost immediately. Thankfully, this can't really happen. Here's the good news. Nothing in nature could stop Earth's spin instantly. Our planet's rotation comes from the conservation of angular momentum, left over from the swirling cloud of gas and dust that formed the solar system billions of years ago. Stopping it would require an enormous, sudden external force. We actually have physical proof that Earth rotates, without even looking at the sky. In 1851, physicist Léon Foucault suspended a giant pendulum in Paris and showed that its swinging plane slowly rotated relative to the floor, direct evidence that the floor, and the whole building, was turning beneath it. Today, scientists track Earth's rotation with incredible precision, precise enough to notice that it occasionally speeds up or slows down by fractions of a second due to earthquakes, glacial melt, or shifting mass inside the planet. Timekeepers even add leap seconds occasionally to keep our clocks synced with Earth's real spin. So instead, let's imagine the more realistic version, a gradual slowdown over hundreds or thousands of years, similar to how the moon's gravity is already slightly breaking our rotation today, just far more extreme and rapid. This version wouldn't destroy us in an instant, but it would completely reshape our world. Interestingly, this is already happening, just unimaginably slowly. Tidal friction from the moon is lengthening our day by about 1.7 milliseconds every century. At that rate, it would take many billions of years to fully stop Earth's spin, long after the sun itself would have changed dramatically. But for the sake of this thought experiment, let's fast forward and imagine Earth has fully stopped rotating relative to the sun. The first and most obvious change, our 24-hour day is gone. Instead, since Earth still orbits the sun once a year, each hemisphere would experience one extremely long day and one extremely long night. That means roughly 6 months of continuous daylight followed by 6 months of continuous darkness for any given location. Depending on its position relative to the sun's sunrise and sunset, as we know them, would essentially disappear, replaced by seasons of light and seasons of endless night. During the 6-month day, temperatures in exposed regions would climb to extremes, since the ground would have months to absorb solar energy without a nightly cool down. Deserts could become blisteringly hot, potentially uninhabitable. Meanwhile, the 6-month night would allow temperatures to plunge far below anything we experience in modern winters. This extreme temperature swing wouldn't be gentle. Without rotation constantly mixing warm and cold air masses through day-night cycles, heat would build up dangerously on the sunlit side, while the dark side would radiate its warmth into space, unreplenished, growing colder and colder as the long night dragged on. Agriculture as we know it would collapse. Crops rely on daily light cycles for photosynthesis and growth rhythms. A 6-month day followed by 6-month darkness would devastate most plant life, forcing any surviving agriculture into greenhouses, artificial lighting systems, or migration toward the narrow twilight zones between day and night. Speaking of twilight zones, there's a narrow band on a non-rotating Earth, the terminator line between permanent day and permanent night, where temperatures might stay relatively moderate. Some scientists speculate this thin ring around the planet could be the most habitable region left, similar to the concept of tidally locked exoplanets. This idea isn't just theoretical. Astronomers already study tidally locked exoplanets, worlds that always show one face to their star, for exactly this reason. Their narrow twilight zones are considered prime candidates for hosting life, because they avoid the extreme heat of the day side and the extreme cold of the night side. Now let's talk about Earth's shape, because rotation isn't just about day and night. Our planet isn't a perfect sphere. Centrifugal force from spinning causes Earth to bulge slightly at the equator and flatten slightly at the poles, making it what scientists call an oblate spheroid rather than a perfect ball. That bulge is significant. The equatorial radius is about 21 kilometers larger than the polar radius. It exists because outward centrifugal force at the equator slightly counteracts gravity there, roughly 0.34% of your normal weight. Without rotation, that force vanishes entirely, and the whole planet would begin reshaping itself. As the bulge relaxed over time, gravity would pull Earth toward becoming a perfect sphere. This isn't just a cosmetic change. It means the crust itself would shift, generating enormous stress. Regions that were once stable could experience new fault lines, increased earthquake activity, and possibly new volcanic eruptions. And here's a wilder detail. Earth's molten outer core doesn't necessarily stop spinning at the same rate as the surface. If the crust and mantle slowed while the liquid iron core kept moving with more momentum, that mismatch could churn the interior violently, potentially triggering unpredictable volcanic activity in unexpected places. This mismatched core motion matters for another huge reason: our planet's magnetic field. Earth's magnetic field is generated by the geodynamo, the churning motion of molten iron in the outer core, driven largely by the planet's rotation. Disrupt that rotation, and you disrupt the engine that protects us from space. As rotation slowed, the geodynamo would weaken, and so would Earth's magnetic field. That field normally deflects harmful solar radiation and cosmic particles, and it's also responsible for beautiful auroras near the poles. A weakened field means more radiation reaching the surface and potentially auroras appearing at much lower latitudes. To understand why rotation matters so much here, think of the geodynamo like a bicycle generator. Movement, in this case the churning of molten iron combined with Earth's spin, generates electric currents, and those currents generate the magnetic field. Slow the movement, and the generator simply produces less and less power over time. A weaker field wouldn't just mean prettier auroras at strange latitudes, it would mean real health risks. Increased cosmic radiation and solar particles reaching the surface could raise cancer risks over time and would pose serious dangers to electronics, satellites, and any astronauts or aircrews traveling at high altitudes. Over time, a severely weakened magnetic field could allow solar wind to strip away parts of our atmosphere, similar to what scientists believe happened to Mars billions of years ago. Mars once had a magnetic field and a thicker atmosphere, but when its core cooled and the dynamo stopped, the atmosphere thinned dramatically. This doesn't mean Earth would become Mars overnight, but it's a sobering comparison. A weakened magnetic field combined with atmospheric loss over long timescales could make the planet increasingly hostile to life, layering yet another slow-motion crisis on top of the temperature extremes and reshaped geography we've already covered. Let's return to the oceans, because a stopped Earth doesn't just change day and night, it redraws the map entirely. As the equatorial bulge flattens, all that extra water currently held near the equator has nowhere to stay. Gravity pulls it toward the poles instead, seeking a new equilibrium shape. ESRI, a geographic technology company, actually modeled this scenario. Their simulations show water rushing away from the equator and pooling around the poles, creating two enormous new polar oceans, while land around the equator, no longer submerged, would be exposed as a vast new supercontinent connecting old, separated landmasses. Cities like Miami, Mumbai, and Dhaka, all low-lying and near the equator, could end up on newly exposed land rather than coastline, since the ocean would have retreated toward higher latitudes. Meanwhile, regions closer to the poles that are currently dry land could find themselves underwater for the first time. This redistribution wouldn't happen overnight either. It would unfold over decades to centuries, as oceans slowly seek their new resting points, and the crust elastically adjusts to the changing weight distribution. But by the end of it, the atlas of our world would be almost unrecognizable compared to today. Ocean currents would suffer too. Right now, a global system called thermohaline circulation, sometimes nicknamed the ocean conveyor belt, moves warm and cold water around the planet, partly steered by rotation and wind patterns. Without the Coriolis effect guiding these currents, this circulation could stall or reroute entirely. A stalled ocean conveyor belt would be devastating on its own. This circulation currently helps regulate regional climates, keeping places like Western Europe far milder than their latitude would otherwise suggest. Disrupting it could plunge some regions into unexpected cold snaps, even while other areas broil under constant sunlight. Polar ice would also behave unpredictably. With new oceans pooling at the poles and 6-month nights allowing intense cooling, we might expect thickening ice caps there. But the 6-month polar days, combined with weaker climate regulation, could also trigger dramatic melting cycles, causing repeated flooding and freezing in those same regions. Now let's talk about weather, because rotation doesn't just shape oceans and land, it shapes the wind. Right now, Earth's spin creates something called the Coriolis effect, which deflects moving air and water, curving winds and currents rather than letting them travel in straight lines from hot regions to cold ones. The Coriolis effect is why hurricanes spin, why trade winds blow in consistent patterns, and why jet streams snake across the upper atmosphere in organized bands. Without rotation, none of that structure would exist. Air would simply rush directly from the boiling hot day side toward the freezing night side. This direct, unmoderated airflow could generate extraordinarily powerful and prolonged storm systems, potentially reaching speeds near or beyond the speed of sound in some models. Unlike our current hurricanes, which eventually dissipate, these storms could persist for weeks or months, since the temperature difference driving them never really lets up. Weather forecasting as we know it would become meaningless. Instead of rotating storm systems moving predictably across regions and days, we'd face slow, massive, persistent weather monsters camped over the same areas for extended periods, alternately flooding some regions for months and leaving others parched and dry for just as long. It's worth pausing here to appreciate just how much our daily comfort depends on rotation. The 24-hour cycle regulates our sleep through circadian rhythms. It regulates plant growth cycles, animal migration and hibernation patterns, and even ocean ecosystems that depend on predictable light and temperature changes throughout each day. Nearly every living organism on Earth has evolved around that daily rhythm. Remove it, and you're not just changing the weather or the map, you're pulling the rug out from under billions of years of biological evolution. Life could potentially adapt over immense timescales, but the transition would be devastating. Human timekeeping itself would need to be reinvented. Calendars, clocks, and even religious and cultural traditions tied to sunrise and sunset have shaped human history for thousands of years. Without a daily sunrise, entire systems of measuring time, scheduling work, and organizing society would need to be rebuilt from scratch. Animal migration would be thrown into disarray as well. Countless species rely on day-length cues to know when to migrate, breed, or hibernate. Birds that fly thousands of kilometers based on seasonal daylight changes, or coral reefs that spawn in sync with lunar and daily light cycles, would lose those critical signals entirely. There's also a subtler effect worth mentioning: your weight. Right now, the outward centrifugal force at the equator slightly reduces your effective weight compared to the poles by about 0.3%. If rotation stopped, that effect would vanish, and everyone on Earth would weigh very slightly more than before. It sounds like a minor detail compared to tsunamis and superstorms, but it's a good reminder that rotation touches almost every physical aspect of our planet, from the shape of the globe to the weather in the sky to the exact number on your bathroom scale. Nothing about Earth is untouched by its spin. Space travel would also be affected. Currently, rockets launched eastward near the equator get a helpful speed boost from Earth's rotation, saving significant fuel. Without that spin, every rocket launch would need more fuel and more energy to reach orbit, since that free velocity boost simply wouldn't exist anymore. GPS and satellite systems would also need significant recalibration. These systems rely on extremely precise models of Earth's rotation and shape to function accurately. A reshaped, non-rotating Earth would require entirely new navigational math, and existing satellites in orbits designed around Earth's current rotation could face long-term instability. Global infrastructure built around the 24-hour cycle would also need reinvention. Power grids currently balance electricity demand between day and night usage patterns. Aviation routes are planned around daylight and predictable jet streams. Even international time zones, an entire coordination system for global business, would become completely obsolete. Solar power, ironically one of our most promising clean energy sources today, would become far more complicated. 6 months of continuous sunlight could generate enormous energy surpluses in some regions, while 6 months of darkness would leave the same regions completely without solar power, requiring massive long-term energy storage solutions. Now, could life actually survive all of this, given enough time? It's a fascinating question. Extremophiles, organisms adapted to extreme heat, cold, radiation, and pressure, already exist on Earth today, thriving in places like deep-sea vents and Antarctic ice. Life on a stopped Earth might follow a similar path. Over many generations, some species might migrate toward that narrow twilight zone between eternal day and eternal night, where temperatures stay moderate. Others might adapt to extreme heat or cold directly. It's plausible that entirely new ecosystems could emerge, radically different from anything currently found on our planet's surface. Human civilization, though, would face a much harder path than evolving new biology. We'd likely need to cluster populations near that twilight zone, build enclosed and climate-controlled cities, and develop entirely new agricultural systems using artificial lighting to replace the daily cycles our crops have always depended on. This kind of adaptation isn't pure fantasy. Engineers and scientists studying long-duration space habitats and potential colonies on the Moon or Mars already design systems around artificial day-night cycles, radiation shielding, and controlled agriculture, essentially rehearsing the same technologies a non-rotating Earth's population might eventually rely upon. It's a strange thought. Surviving a stopped Earth might require the exact same technology we're already developing for surviving other, naturally non-rotating or tidally locked worlds. In some ways, studying this thought experiment helps scientists better understand what it might take to live on entirely different planets someday. If we zoom out and think about cost, the economic toll of even a gradual rotational slowdown would likely dwarf anything in recorded history, far beyond the combined cost of every war, pandemic, and natural disaster combined, simply because it would touch agriculture, energy, transportation, and coastal real estate all at once, globally, permanently. Insurance systems, global trade routes, and food supply chains, all built around predictable seasons and stable coastlines, would need to be entirely reimagined. Some economists studying similarly extreme climate disruption scenarios suggest that societies might eventually stabilize, but only after generations of extraordinarily difficult and costly adaptation. So, could this scenario actually happen naturally? As we mentioned earlier, the honest answer is no, not suddenly, and not without an extraordinary external force. Earth's spin is simply too much angular momentum, roughly 2.1 times 10 to the 29th joules of rotational energy, for anything short of a planetary-scale collision to stop. Even a giant asteroid impact, similar in scale to the one that ended the age of dinosaurs, wouldn't be nearly powerful enough to halt Earth's rotation. It would cause massive regional devastation, certainly, but Earth's spin is simply too enormous a quantity of momentum for a single impact event to erase. Realistically, the only forces capable of significantly altering Earth's rotation over any meaningful timescale are gradual ones, like the Moon's tidal pull, which is already slowly lengthening our days, millisecond by millisecond, century by century, a process that would take many billions of years to fully play out. This slow tidal process is actually how many moons in our solar system became tidally locked to their planets in the first place. Our own moon is a perfect example. It always shows the same face to Earth because its rotation and orbit have already synced up completely, a process that took billions of years. In theory, if given enough time, far more time than the Sun has left in its current stable phase, Earth could eventually become tidally locked to the Sun the same way our moon is locked to us. But as we've mentioned, other cosmic events would almost certainly reshape the solar system long before that happened. In fact, some scientists believe that long before Earth's rotation could ever fully stop through natural tidal processes, our Sun will have already evolved into a red giant billions of years from now, likely engulfing or dramatically altering Earth long before rotation becomes the planet's biggest problem. So this thought experiment really exists in a comfortable, purely hypothetical space, useful for understanding physics, geology, and planetary science, but not something anyone needs to genuinely worry about happening. It's a thought experiment, not a prediction, and that's exactly what makes it such a fascinating one to explore. Let's take a moment to summarize what we've covered so far. A sudden stop would be instantly catastrophic, supersonic winds, planetary tsunamis, and total ecological collapse within minutes. A gradual stop, while more survivable, would still reshape our climate, our geography, our magnetic field, and possibly our biology forever. We'd lose our familiar 24-hour day, replaced by 6-month cycles of light and darkness. We'd lose our current coastlines, replaced by a new supercontinent near the equator and 2 vast oceans at the poles. We'd lose the Coriolis effect, replaced by chaotic, unrelenting, planet-spanning storm systems. We'd likely see a weakening magnetic field, exposing the surface to more radiation and more spectacular, but concerning auroras at lower latitudes. And through it all, life, if it survived at all, would likely cluster into the narrow, temperate twilight zone between Earth's permanent day and permanent night sides. It's also worth remembering that none of these consequences are equally distributed. Communities near the equator, near coastlines, or in regions already vulnerable to extreme weather would face the harshest and most immediate impacts, while populations near the twilight zone or at higher, more stable elevations might fare comparatively better. It's genuinely remarkable how much of what we take for granted, comfortable temperatures, reliable weather, a working compass, a protective magnetic shield, GPS accuracy, even your exact body weight, all traces back to one simple fact. Our planet spins on its axis roughly once every 24 hours. That rotation isn't just a neat astronomical fact. It's the invisible foundation that our entire climate, ecosystem, and civilization is built upon. We rarely think about it because we've never experienced anything else, but this thought experiment shows just how fragile that foundation actually is and how much we depend on it. It's also a great example of how interconnected planetary systems really are. One single variable, rotation, touches weather, geography, biology, magnetism, and even how much fuel a rocket needs to reach space. Change that one variable, and dozens of seemingly unrelated systems shift in cascading, unpredictable ways. This is also why scientists study extreme hypothetical scenarios like this one in the first place. By exploring what would happen if a key variable disappeared entirely, researchers gain a deeper understanding of exactly how important that variable is to the systems we currently depend on and often overlook. It's the same reason astronomers study tidally locked exoplanets, worlds that never rotate relative to their star. Understanding how those alien worlds might support life in narrow twilight zones actually helps us better understand our own planet's relationship with something we usually never think twice about, our comfortable, familiar spin. So the next time you watch a sunset, or set an alarm for tomorrow morning, it's worth remembering that this simple daily rhythm is the product of an enormous, ancient, invisible force, angular momentum from the birth of the solar system, quietly keeping our entire planet's systems in careful balance. To wrap up, a stopped Earth would mean supersonic winds and catastrophic tsunamis if it happened suddenly, or 6-month days and nights, reshaped continents, weakened magnetism, and chaotic weather if it happened gradually. Either way, our familiar blue planet would become something almost entirely unrecognizable to us today. Thankfully, none of this is something we need to lose sleep over. Earth's spin is remarkably stable, protected by immense angular momentum that no natural force realistically threatens on any timescale relevant to us. But exploring the question does something valuable. It makes the ordinary feel extraordinary again. So here's a question worth sitting with. Of everything we covered today, the tsunamis, the 6-month days, the reshaped continents, the fading magnetic field, which consequence do you think would be hardest for humanity to actually adapt to and survive over the long run? Let us know what you think. If you enjoyed this deep dive into planetary physics, there are countless other what-if scenarios worth exploring. What if the moon disappeared? What if Earth had 2 suns? Or what if our planet's magnetic field vanished entirely, right now, without any change to rotation at all? The universe is full of fascinating questions. Thanks for exploring this thought experiment with us today. Understanding these extreme, hypothetical scenarios helps us appreciate the delicate, invisible systems keeping our real world stable and livable, systems we rarely think about, but that quietly shape absolutely everything about our daily lives, our climate, and our future.